So in Chapter 10 for CCENT, we'll be talking about subnetting. And we'll actually be looking at subnetting from two different perspectives. We're going to be looking at subnetting from IPv4's perspective, and we'll be looking at subnetting from IPv6 perspective. We talked about yesterday quite a bit about how IPv6 addresses are organized and the fact that subnetting does exist, although it may not be in the same fashion or form that you would see for IPv4. The general concept of subnetting is very simple. We're taking large networks and we're dividing them up into smaller networks, right? And this came from the concept of when we had classful addressing, where we had Class A, Class B, and Class C subnets. Well, the Class A subnets were just, or networks were just too large to be practically usable in a routed environment. So it was much better for us to take that large Class A network and divide it up into smaller networks. Now, mathematically, the concept of subnetting is very simple. What are we changing? Excuse me. What are we changing to create subnets? Whether it's IPv4 or IPv6, what are we actually changing to create subnets? Any ideas? The subnet mask. The subnet mask. That's right. We manipulate the subnet mask to create these different types of networks. And of course, I'm going to teach you guys how to do that as part of our process here. We also know that for every router interface that we have to have a unique subnet. You can't put the same network on two different router interfaces. Otherwise, it might as well be a switch. So it allows us to manage the size of our networks. It allows us to physically locate networks in different locations and so on. When it comes to subnetting, there are only 5 things that you will ever have to know. And by the way, on the test, if you get subnetting questions on the test, which you will, if you get subnetting on the questions on the test, it doesn't matter how the question is worded, what type of format they have, it's going to be one of these 5 things. All right? And I'm going to teach you guys how to calculate all 5 of these things as we go through the process. First of all, if I give you an IP address and a mask, what is the network ID for a host? That's the first question. Remember what the network ID was by definition? It's the room that the host belongs to, right? If I give you an address or mask, what is the broadcast ID for that host? Of course, we only have that in IPv4 because we don't have broadcasting in IPv6. All right. We know it's the last IP. We know the network ID is the first IP. What I'm talking about, though, is having the ability to get an address and a mask and to calculate what the actual values are. What are the usable host addresses in the subnet? In other words, how many addresses can I actually use? And not only how many addresses can I use, but what are they? Is it 10.1 through 10.62? Is it 10.1 through 10.126? What is it? Question number 4, how many subnets did I create with that mask? And question number 5, how many total addresses are assignable? All right. Now I'm going to show you guys something real quick here. Let me go ahead and pull up Notepad. All right. And I want to give you an idea of what it is that you will be able to look forward to as we progress through this chapter here. Now, what I would like somebody to do is to give me an IP address that is completely random. Don't do 10.10.10.5 or 192.168.5.10. I'm talking about a completely random address. Could be private, could be public. Give me one octet.
192.168.150.170.
You're doing exactly what I said. Okay, all right. Fine, we'll go with that.
Okay, sorry. Okay.
Completely random.
150.174.
150.174.129.19. Yes, that's very random. Thank you. All right. Okay. Now somebody give me a mask, and don't make it in a major boundary. Don't give me a /24 or a /16. / something, but not on a major boundary. /13. Okay. /13. I'll do the one that you guys put on there online in a second here. Now, the purpose of this, I'm not doing this so that you guys can learn how to do this. I'm doing this to show you what you're going to be able to do after you go through this discussion. So this is pretty typical. I might get an address and a mask, and I'm going to say, okay, what is the network ID for that host? What is the broadcast ID for that host? What is the host range? In other words, what are the usable addresses and so on? All right? So if I look at this address, okay. If I look at this address, I can tell you, all right, that, well, I can tell you a few things about this particular address. First of all, I know that the network ID, broadcast ID start with 150. That's simple enough. There's no real math that you have to use with that. But I know from a /13 that my networks are a certain size. I know that they fall within certain block ranges, right? Which means in this case, they're blocks of 8. So I know that, for example, a network is 80, and then another network is 88, another network is 96, another network is 104. I think it's 104. What's 96 plus 8? Is that 104? Yep. Right? I know another network is 112. I know another network is 172. Oops, sorry, 120, right? And so on. Because I know that those networks are blocks of 8, and you guys have no idea how I figured that out yet. You may, okay? But the point of this discussion is not to teach you that. The point of this discussion is to show you where we're going to get to when we get to the end of this discussion, is I can identify very easily, just by knowing the subnet mask and the address, all of the components of that address, right? 160 is a network. 168 is a network. Now we're getting close to our network, all right? Then we've got 170, what is it, 174? All right? So the network ID for my host is 150.174.0.0. The broadcast, what's the next network after 174? 182? 176, yes, sorry. All right. So actually, we went past, right? So the network for our host is 168. So the next network is 176, which means that for this particular address and mask, the network ID is 150.168.0.0. The broadcast is 150.175.255.255. And the host range is 168.0.1 through 175.255.254. Shoot, there we go. Okay. Now, this process that I used in my head, right? I didn't do any binary math. I didn't do any logical ANDing or logical ORing or converting bits to ones and zeros. I basically looked at the subnet mask and I said, okay, based on this subnet mask, I know what the makeup of the network is. Okay? Somebody gave me one online of 67.24 12.209, all right, /28, all right. Now I can already tell you right now the network ID for that address is 67.24.12.192, all right. And the broadcast is 67.24.12 dot, let's see, it's blocks of 30, it's blocks of 16. Well, anyway, I'll show you guys how to do this process, okay? All right, any mask, any address, same process, same calculation, all right? We'll come back to this one in a little bit. In fact, I'm going to leave this one up on the slide here to show you how we do the calculations individually. But this is a progression, right? As with anything that involves math, you need to kind of learn the process. But I guarantee you, if you apply this process every time, you can answer any one of these 5 questions with very little effort. Very little effort. All right? So let's get into some of the kind of the foundation stuff, and then we'll get into some of the calculations. We already talked about the concept of classful versus classless. Classful networks, Class A, Class B, Class C. We know what the purple boxes represent. Those are my major network boundaries. The kind of pink-looking boxes represent the host portion. The concept of subnetting, though, and this is what's really important to understand. The concept of subnetting is making the purple larger and the pink smaller. And we do that by shifting where the ones are and where the zeros are. The more ones there are in a mask, the fewer hosts can exist in the network. You guys agree with that? The more ones there are in the subnet mask, the fewer hosts exist in the network. The more zeros in the mask, the more hosts in the network. Mathematically, we'll see how that's calculated here in a little bit. But would you guys agree that we can have a lot less hosts in a Class C network than we can have in a Class A network? Right? The concept of subnetting is what we call borrowing bits. You'll see this term as we kind of go through our discussion here. Borrowing bits, meaning stealing zeros and making them ones. And every time you steal a 0 and make it a 1, you're creating a subnet. And this applies to both IPV4 and IPV6. Every time you steal a 0 and make it a 1, you're creating subnets. All right? We have to go full circle here. And this discussion, it's important to understand that we kind of run through a building process here. This is not just, these are the formulas and this is how you do it. You have to build up to the end, the crescendo at the end, right? So the first calculation that I'm going to teach you guys is this calculation. I'm only going to teach you 3 calculations. And with those 3 calculations, you'll be able to do any subnetting calculation that you want. All right? To calculate the new mask based on what? Based on subnets, we simply count the number of borrowed ones. All right? Let me explain what I mean. You go into the company says, we have this Class A network. I want you to create 100 subnets from this Class A network. I don't care what the size of those networks are. In fact, make them as large as you can, but I need at least 100. We use this formula to calculate that. All right? In fact, let's go ahead and look at an example here. All right? I'm going to leave that one up there for now. So I have this network. 10.0.0.0/8. Okay, you guys remember what the /8 represents?
8 ones.
8 ones in the mask. Is this classful or classless? Is this a classful network or is this a classless network? Right now it's classful. It's a Class A with a Class A mask. I need to create 100 subnets. So what is my new mask? All right, that's a rhetorical question because I'm teaching you this now. Some of you may already know how to do this. The only thing bad about subnetting is if you take 10 different networking classes that teach subnetting, you'll learn subnetting 10 different ways. But ultimately, if you break it down to its binary components, if you break it down to the octets or the hextets, if you're talking about IPv6, it's very, very simple. This is the formula that we use if we're calculating based on the number of subnets. 2 to the power of n equals subnets, period. And n equals the number of borrowed ones. That's literally the entire calculation. 2 to the power of n equals how many subnets you're creating, and n is simply how many bits you're borrowing. How many bits do I have right now in the mask? How many bits do I have right now in the mask? How many bits, how many ones do I have in the mask? 8. There are already 8 ones in the mask. Does everybody agree with that? Yes? Okay, /8, we know that's 8 ones. 2 to the power of n has to be greater than or equal to 100. Why? Why 100?
Because I need 100 subnets.
I need 100 subnets. The formula is 2 to the power of n equals the number of subnets. Now I put greater than or equal to because this is binary math. We're using a radix scale to do our calculations. So we may or may not be able to get exactly 100. Now all you have to do is solve for n. 2 to the power of 5. That equals 32. That's not enough. 2 to the power of 6 equals 64. That's not enough. 2 to the power of 7 equals 128. That's enough. Agree? It's more than enough. We can't get 100 exactly because we're using binary math. Now, 8 means I have to borrow 8 more ones than I had originally. So what is my new mask? /16. Does that make sense? /16. How did I get /16? Huh?
We already have 8, and then we borrowed 8 more.
Oh, yeah, I made a mistake. I apologize. Thank you for pointing that out. Somehow I went from 6 to 8. You guys didn't even notice that. I meant 2 to the 7, right? So the 7 means I need to borrow 7 more ones, which is a /15. Sorry about that. I don't know how I got that 8 in my head. I was going down the right road. 2 to the 5 is 32, 2 to the 6 is 64. So 2 to the 7 must be 128. Somehow I jumped to 2 to the 8. But the concept is still the same. I need to borrow 7 bits to give me 128 subnets. Does that make sense? Now, I'm going to ask the question again. How did I get /15? How did I get /15? Well, my original mask already had 8 ones. I am stealing another 7 ones. Does that make sense? Which means 8 plus 7 is 15. Does that make sense? Now, what does that translate to? Because this is the part that people have an issue understanding, right? What does that translate to? What does that mean for my networks? Well, we're going to learn about the anatomy of our networks later. In other words, okay, I know that my network is, my first network is 10.0.0.0/15, but what is my next network? And what is the network after that? And what is the network after that? I'm going to show you guys how to calculate that in a little bit. All right? And we're going to be doing lots of examples. Hopefully I won't make any more stupid mistakes like I just made, but you know, we're all entitled, I suppose. All right? So let's say, let's do a couple more examples. I have a network of 192.168.10.0/28. I need to create 5 subnets. Now, is this classful or classless? This is classless. Why is it classless? Because it's already a subnet. This is already a subnet, right? You okay over there? Because a 192.168 address is normally a /24, but we have a /28. But there's nothing to say that you can't subnet a subnet. You're allowed to subnet subnets. I need 5 subnets, so I do the math. 2 to the power of n has to be greater than or equal to 5. If I say 2 to the power of 1, that's going to equal 2. If I say 2 to the power of 2, that's going to equal 4. That's not enough. But if I do 2 to the power of 3, that's going to equal what? 8. Right? Every single one of those exponents is simply the number of bits that I'm stealing. The first one represents I'm stealing 1 bit, but that's only going to create 2 subnets. If I steal 2 bits, that will create 4 subnets. If I steal 3 bits, that's going to create 8 subnets, which means my new mask is /what? 31. Because that equals 28 plus 3, which is what I stole. Okay? Not 36. That wouldn't be possible in this case. Remember, we're not adding 8. We're adding the number of borrowed bits. 8 is the number of networks we're creating. 3 is the number of borrowed bits. So it's 28 plus 3. Yep, I saw what you did there when I saw your answer there in the chat. You're taking you know, a page from my book and not paying attention, right? This is a very simple concept, right? It doesn't matter if it's IPv6. It doesn't matter if it's IPv4. The math is still the same. Okay? I have a network of 2001:DB8:1:/64. Let's do, in this case, actually let's do /48. Okay? We have a question in the chat. A statement. If I understand well, /8 to /15 belongs to class A, 16 to 23 class B, and so on. No, not really. Not really. Yes, /8 to /15 is a subnetted class A, but it also could be a supernetted class B. So the only class definitions we really see are /8, /16, and /24. That's what we typically will tie to a class distinction. Anything outside of that is either a supernet or a subnet. Now, prior to coming into this class, You might have thought that you would never be doing subnetting with IPv6, but guess what? It's no different. I have this network. I need to create, I need to create 500 subnets. Now, you don't typically subnet this way in IPv6, but mathematically you can. It's simple. 2 to the power of n has to be greater than or equal to 500. That's the number of subnets that I'm trying to create. I didn't miss the 0 in DB8 because I wrote the shorthand version. Remember, leading zeros in IPv6 are not necessary. It's still there. I just didn't write it down. So 2 to the power of 7 is equal to what? 128. So 2 to the power of 8 is equal to what? 256. And 2 to the power of 9 is equal to what? 512. You guys agree with that? Well, if my original mask is /48 and I'm adding an additional 9 bits, what's my new mask? Right. It's the same concept. Works exactly the same way. All right? It's all binary math. Whether the address is written in hex or whether it's written in decimal, ultimately the math is based on binary. Yes, sir?
I'm still having a hard time on this.
Okay.
Even simple math, I'm sorry, I'm not a math person, but I'm just having a hard time. What does it mean in the first example, 2 to the power of 8, 2 to the power of 5 equals 32? What does it mean?
If you take 2 to an exponent of 5, 2 times 1, or 2 times 2, 2 times 2, 2 times 2, 2 times 2, 5 times, you get 32. 2 to the power of, it's just math. 2 to the power of 5 is 32.
All right.
2 to the power of 1 is 2, 2 to the power of 2 is 4, right? What is 2 to the power of 4, or 2 to the power of 2? It's 2 times 2. What is 2 to the power of 3? It's 2 times 2 times 2. Well, 2 times 2 times 2 is 8. You see what I'm saying?
If you look at like what do you have before, the 2 to the 7, and then you look at 2 to the 8, you can see that 2 to the 8 is twice the amount of 2 to the 7.
Right.
It's pretty much just like.
And by the way, I'm using Notepad, so I can't write the exponents like exponents. That symbol, that caret symbol, means exponent, right? That's just a different way of writing an exponent. So basically, when I say 2 to the power of 7, I'm saying 2 times 2 times 2 times 2 times 2 times 2 times 2. And if you do 2 times 2 times 2 times 2 times 2 times 2 times 2, you get 250 or 128.
Got it.
Okay? And by the way, this is it's just the way it's calculated. Why did I come up with this formula? I didn't come up with this formula. This is how it's done. Every time you borrow a bit from the original mask, you're creating subnets. The number of bits you borrow will determine the number of subnets you create. All right? Now, they might ask you a different question. They might say, well, I have this, 10.10.10.0/26. Actually, let's not do that. That would be, I'm trying to keep you guys away from having to do serious powers of 2, but I have this, 192.10.10.0/26. How many subnets did I create? Okay? Well, in order to know how many subnets you created, you need to know what you started with. Because in order to calculate the bits you borrowed, you needed to know how many bits you had in the beginning. I didn't tell you how many bits you had in the beginning on this one. I just gave you an address and a mask. What does the 26 represent? 26 ones in the mask. What class address is that?
Classless.
Well, that's a classless network as it is right now. But what class is 192?
It's class C.
Class C. And what is the normal mask for 192? Class C, I mean. What is the normal mask for Class C? 1/24. Right? Class C has a normal mask of /24. Class B has a normal mask of /16. Class A has a normal mask of 8. So I'm making the assumption here that I borrowed 2 bits. I'm completely making that assumption based on the fact that I didn't tell you what you started with. I didn't say you started with, and that's why I said, that's why I changed this from a 10, because if that was a 10, then I would have borrowed a lot more than 2 bits. I would have borrowed 18 bits instead, but I didn't want to have to deal with 18 bits. So, and yes, we created 4 subnets by borrowing 2 bits, because 2 to the power of 2 equals 4. 2 is the number of bits that I borrowed. 4 is the number of subnets that I created. Now, this doesn't work with IPv6 because we don't have class distinctions in IPv6. So if somebody tells you, this is my address and mask in IPv6, I suppose you could make the assumption that you started with /48 because that's what most ISPs are assigning, but that's not always guaranteed. All right. Let's see. (172.16). Oops. Well, I don't even. I'll just leave that. I need to create 50 subnets from this address, 172.16.0.0. What mask would I go ahead and assume that I'm starting with?
172 is 16.
16, right? You guys agree with that? Because 172 is class B.
B, yeah.
Right?
So I need 34 bits.
You need 34 bits? There aren't 34 bits. A mask is only 32 bits long. Question is, how many bits do I need to create my 50 subnets? Just remember the formula. 2 to the power of n is greater than or equal to 50. 50 is the number of subnets I need to create. 50 is the number of subnets I need to create. If I solve for the formula, 2 to the power of 5 is what? 32. 2 to the power of 6 is 64. 2 times 2 times 2 times 2 times 2 times 2. 64. So I need 6 bits. 3 bits or 5 bits isn't going to do it. If I borrow 5 additional bits, I'm only going to create 32 subnets. If I borrow 6 bits, I'm going to create 64 subnets. What was my original mask? /16. /16 plus 6 equals /22. Here's the analogy. I need to make clear that you understand what we're doing here. All right? In fact, let me go back to my slide deck here. This is a meeting space in a hotel. Okay? And you know how often meeting spaces in hotels, they have these dividers. There's one right here that you can open and close if you want to make the space bigger or you want to make the space smaller, right? This is one network. By borrowing a bit, you're essentially putting up that divider. You're now making that one large meeting space 2 meeting spaces. By borrowing a second bit, you're now creating 4 meeting spaces. That's the concept of subnetting, taking a large network. But going back to our diagram here, how many people can that meeting space hold? 100 people? How many people can those 2 meeting spaces hold? 50 people. How many people can those meeting spaces hold? 25 people. So every single time you're borrowing a bit, you're creating smaller networks, but you're creating more of them. Does that make sense? That is the concept that we're talking about here. That 6 is just the number of bits we're borrowing. Every time we borrow another bit, we're creating more networks. And they can only be created in powers of 2 because it's a powers of 2 math. It's binary math. Now you can show us how the 24, 16, 8 translate to an actual number. Okay? Yes, I can show you that. In fact, I'll show you that for part of the next example. You would like to know, Derek wants to know how we get from a /16 to a 255, 25500. And I'll show you guys that. All right? That is the first calculation. That is the first calculation. Calculating your mask based on the number of networks that you need. Now, we're also assuming in this case that we're using simple subnetting. Simple subnetting means that all of the networks are the same size. There's another type of subnetting we'll talk about towards the end of the chapter called VLSM, where the networks are not the same size. It gets a little bit more complicated, but the math still holds true. What if I don't want to calculate my networks based on the number of networks, but I want to calculate based on the number of hosts? Well, we'll get into that next. Here's a couple of examples. I'm given an address of 172.16.10.0/24. That's already a subnet. Agreed? All right. I need to create 10 subnets from this address. 2 to the power of n has to be greater than or equal to 10. I calculate for n. In this case, it's 4. That's just what it is, because 2 to the power of 3 is 8. 2 to the power of 4 is 16. We have 24 ones in our original mask. That's what we were given originally. We're borrowing an additional 4 ones, so my new mask goes from 24 to 28, because 4 plus 24 is 28. All right? How do we get that converted to that? 28 ones, right? 1, 2, 3, 4, 5, 6, 7, 8. 255. Dot. 1, 2, 3, 4, 5, 6, 7, 8. So that's 16 of them. 255. 1, 2, 3, 4, 5, 6, 7, 8. That's 24 of them. 255. 25, 26, 27, 28. Right? Isn't that 28 ones? Mm-hmm. This becomes 240. How does that become 240? Because this is the 128 column, 64, 32, and 16. 128 plus 64 plus 32 plus 16 is 240. All right. I am given the address of 10.21.00/19. Already a subnet. We have this mask, 255.255.240.0. There's 8 ones plus 8 ones, that's 16 ones. I need 19, so there's 3 ones here, which is 128 plus 64 plus 32. That equals 224. All right? I need 103 subnets. 2 to the power of n equals or greater than or equal to 103. Solve for n equals 7. If we have 19 ones originally, we have 7 additional ones. That takes me to a /26. All right? Questions? We're not done. We've got a lot to do, but that's the first of the 3 formulas. Calculating the number of networks based on how many subnets you want to create. And the formula is the same for IPv6 as it is for IPv4. Like I said, what if I want to calculate those same number of subnets, or I want to calculate based on hosts? We do this quite often. We build out our networks based on how many hosts we need per network, as opposed to how many networks we need. We just did this one, number of subnets required. That's the 2 to the power of n equals subnets formula. Number of hosts required, the formula is different. Because when it comes to hosts, what are we concerned about? Let me go ahead and go back to this slide here. When it comes to hosts, what are we concerned about in the mask? Are we concerned about the ones? No. We're concerned about the zeros. The number of zeros in a mask determine how many hosts you can have in a network. The number of ones in the mask determine how many networks. The number of zeros in a mask determine how many hosts per network. That's why I wrote it this way. Kind of burn it into your brain. Hosts, zeros. So if I'm calculating my subnet mask based on hosts, this is the formula. 2 to the power of n minus 2 equals the number of hosts. Now in this case, n means something different. In our first example, n was representing the number of barred ones. But because we're talking about hosts, n represents the number of zeros. We're going to do some examples. Make it more clear, hopefully. In fact, let's go ahead and do a couple of examples here. I have this 172.16.0.0/16. I need a bunch of subnets, but 500 hosts per subnet. What is my new mask? See, in this particular case, I'm not concerned about how many subnets I'm creating. I'm concerned about the size of the networks. I want to make sure that the networks are large enough to meet my requirement for my hosts. Hold on one second. All right. The formula, 2 to the power of n minus 2 equals the number of hosts. So in this case, 2 to the power of n has to be what? 2 to the power of n minus 2 has to be greater than or equal to 500. Right. Now, we know why we subtracted 2, right? Because in every single network, there are 2 addresses that cannot be assigned to anything, the network ID and the broadcast ID.
Earlier you did an example where the subnet mask ended up being 31, so that leaves us with 2 hosts. Well, 2 hosts.
31 left us with 2 addresses, not 2 hosts.
Yeah.
Right.
Yeah.
So for a normal network, that would not be usable.
Okay.
But for point-to-point serial links, because serial links operate a little bit differently than broadcast networks,
Yeah.
they can use a /31. All right.
So in this case, how would we rewrite it again? It's 2 to the power of 9 minus 2 equals 510.
Right. So 2 to the power of 9. 2 to the power of 9 minus 2 equals 510. Yes? All right. What does 9 represent? 9 is the total number of zeros in my mask, period. We're not talking about borrowed, we're not adding, we're not subtracting. 9 zeros in the mask, period. It's simple. How many bits exist in a mask? Period. How many bits exist in a mask? 32. There are 32 total bits in a mask, right? If 9 of them are zeros, then what must the rest of them be? Ones. Because a mask is only ones and zeros. So if 9 of the bits are zeros, then the rest must be ones. What is 32 minus 9? Hmm?
23.
Go ahead.
23.
23. So my mask is /23. Right? I started with /16, and I ended up with /23. Now I can also calculate how many subnets that gives me, right? Because how many bits did I borrow? How many bits did I borrow? 7. So 2 to the power of 7 is the number of subnets I created. And I know that each subnet supports 510 hosts. Make sense?
Study it at home.
Well, the nice thing is you can go back and watch the video 100 times. All right? So let's look at our examples that we have in our book here, or in our slide deck. I'm given an address of 172.16.10.0/24. That's already a subnet again, but it doesn't matter. How many zeros do I have in my original subnet? I have 8 zeros. We're not talking about decimal zeros. We're talking about binary zeros. And by the way, this formula works for IPv6 as well. But in IPv6, we don't subtract 2. We only subtract 1. Why? Because there's no broadcasting in IPv6. You see what I'm saying? All right. So 2 to the power of 8 minus 2, that's how many hosts I can support in my original subnet. I need 4 subnets, but each of those subnets have to support 35 hosts. Each of those subnets have to support 35 hosts. Put it into the formula. 2 to the power of n minus 2, greater than or equal to 35. Solve for n. What does the 6 represent here? When we're talking about hosts, the 6 represents what? The number of zeros in the mask. The 6 represents the number of zeros in the mask. All right, well, there's 32 bits in a mask. If 6 of them are zeros, then 26 of them have to be ones. All right. I'm given an address of 10.21.0.0/19. So that network has 13 zeros, which means I can have 8,190 hosts per subnet, or in that network, I should say. But now I want to have 420 hosts per subnet. Again, you just simply put it into the formula. 2 to the power of n minus 2 has to be greater than or equal to 420. That means 9. 9 means the number of zeros. 32 bits in the mask, 9 of them are zeros, which leaves us with /23. All right? That's the second calculation. Now, I'm confident that there are a few people online that might be missing this, a few people in the classroom that might be missing this, but it is not overly complex. The thing that you have to understand is you just have to understand what the n represents. When you're talking about subnets, n represents the number of borrowed ones. When you're talking about hosts, n represents the number of zeros. If you can keep that straight and simply remember the formula, 2 to the power of n or 2 to the power of n minus 2, you can do those other two calculations. Now, if we go back to our original slide here, we did which of the 5 things? We did how many subnets and how many total addresses, which is the number of hosts. What we didn't do is this. What is the network ID for the host? What is the broadcast ID for the host? What are the usable addresses? Usable meaning what are the actual usable addresses? This is what I would refer to as the anatomy of a subnet. It's simple enough to say your mask is this, your mask is that, but unless you know where your networks begin and where the networks end, how do you know how to assign them in your topology? Well, the third step that we're going through answers all 3 of those questions by itself. All right? Which is the process that I was going through when we first started this lesson. Okay? It's called the anatomy of the subnet. Okay? This was step 1. We already did that. This is step 2. We already did that. Now we're into step number 3. And when you see how step 3 works, well, quite frankly, you're just going to be subnetting all the time because you're going to love it so much, right? It's very, very simple, all right? Very, very simple. Although it will take a little bit of practice, we're going to go through some examples. Did you say in IPv4 the formula for a host was 2 to the power of n minus 2, IPv6 2 to the power of n minus 1? Yes, that is correct. We subtract 1 in IPv6 because we still have broadcast IDs in IPv6. We subtract 2 in IPv4 because, we don't have broadcasts in IPv6. We subtract 2 in IPv4 because we have a network ID and a broadcast ID. All right. Well, let me show you what I'm talking about. If I have 2001 DB8 ACAD :1 /64. All right. First of all, what does the /64 represent? The subnet mask, right? 64 ones in the mask. Well, that's going to cover those 16 bits. That's 16 bits there. That's going to cover those 16 bits, so that's 32. Those 16 bits is 48, and those 16 bits is 64. You guys agree with that? So how many zeros do I have? If I have 64 ones in the mask, how many zeros do I have? How large is a mask in IPv6? 128 bits. I have 64 zeros, right? 2 to the power of 64 minus 1 equals how many hosts I have in that network. Okay? Again, we're subtracting 1. First of all, we got the 64 because if there are 64 ones in the mask, there must be 64 zeros also. I'm subtracting 1 because of the network ID. And this is a mathematical term for I don't want to calculate 2 to the power of 64, right? Okay. So, the anatomy of a subnet. I gave you a very basic example here. This is our classful network. Excuse me, and we've been tasked, here let me clear off the screen. This is our classful network, and we've been tasked with breaking that network up to support 4 subnets with this number of hosts. Now, if I was using a common subnet mask, meaning every single network has the same subnet mask, would I base it on the 57 or would I base it on the 19? I'd base it on the 57, right? It's like saying if I'm going to break up my meeting space and they're all going to be the same size, if I want 19 people here, I'm not going to make all my meeting spaces big enough for 19. I'm going to make it big enough for whichever the largest group is, right? In this case, 57. So I need 4 subnets, and I need at least 57 hosts per subnet. You guys agree with that? Well, that's what we see here. 2 to the power of 2 gives me 4 subnets. When 2 is the number of borrowed ones, 2 to the power of 6 gives me the number of hosts when 6 is the number of zeros. So we know mathematically this is possible. A /26 solves both problems. It gives me 4 subnets, and it actually gives me 62 hosts per subnet. Well, that's great, but what does that mean for what the networks actually are? All right, so let's do that. Let me pull up my notepad here. 192.168.10.0/24. All right. We have a comment online. If a mask in IPv6 is /64, does that mean we can do no more subnetting? Actually, it does not mean that. For older operating systems, that was the rule, because the older operating systems could only use the EUI64 process. But in IPv6, you can subnet all the way down to 126 or 127, okay? You're not restricted to stopping at 64 in IPv6. You can go lower than 64. Most people just stick around 64 because of the EUI64 process and because of what we talked about in the last lesson. All right? So, if my new mask in this case, we already calculated it, my new mask is /26, which by the way is 255.255.255.192. Everybody should have a good understanding of how we got to 192. All right? The question then is, what are these networks? Where do the networks begin? Where do the networks end? What are the network IDs? What are the broadcast IDs? What are the host ranges? All right? Well, this is how we do it. We calculate something called the block size. First of all, the first question you ask yourself is, what octet am I subnetted in? And can anybody answer that question? Which octet am I subnetted in? The fourth octet, right? You guys agree with that? That's the octet that I borrow bits from, isn't it? So I'm subnetted in the fourth octet. Step 2, take that value of the mask and subtract it from 256. 256 minus 192 equals what? 64. This is where the magic happens. Every address in the fourth octet, because that's what we're subnetted in, divisible by 64 is a network ID. Every octet, or every address in the fourth octet divisible by 64 is a network ID. What's our first network? 192.168.10.0. We always start at 0. What's my next network? Anybody? What's my next network? Every address divisible by 64 is a network ID.
So 192.168.10.65.
64. 65 is not divisible by 64. 168.10.64. 65 is not divisible by 64. At least not as a whole number. What's my next network? 192.168.10.128. What's my next network? 192.168.10.192. Now, if I were to add 64 again, I would get 192.168.10.256. Well, we know that's not possible. Can't go to 256. So by knowing the block size, I was able to calculate each of my network IDs. And by the way, if I know my network IDs, what else do I know? Don't I know my broadcast IDs? By definition, what is a broadcast? What is the broadcast ID by definition? What is a broadcast ID by definition?
The largest IP that's available in that subnet.
It's the last address in the subnet, isn't it? The broadcast ID is the last address in the subnet. Well, if 64 is the next network, what is the broadcast for the previous network? 63. If 128 is the network ID for the next network, what is the broadcast address for the previous network? 127. 192.168.10.191. You guys get the idea. And the last one would be 192.168.10.255. Because the next network mathematically would have been 256. And by the way, if I know what the network ID is, and I know what the broadcast ID is, what else do I know?
The values of the, you know your range.
I know my assignable address range. The assignable address range is everything in between, 192.168.10.1 through 192.168.10.62. So that is network number 1. Network number 2, 192.168.10.65 through 192.168.10.126, right? That's network number 2, 192.168.10.129 through 192.168.10.190, and so on. And then network number 4, 192.168.10.193 through 192.168.10.254. So those are my 4 networks. I know the network IDs, I know the broadcast IDs, I know the host ranges. What addresses can I assign to my router interfaces? Well, I can actually assign any address within the range. I can't assign 0, I can't assign 64, I can't assign 192 or 128, and I can't assign 192. Now, this is not this is not really a new way of looking at subnetting. It's a different way of looking at subnetting. When I originally learned how to do subnetting, I was doing logical ands and logical ors and converting to binary and doing binary math. But let me show you what the real magic of this is, okay? And it does take a little bit of practice to get used to it. Let's take a look at our example here. First thing is, what is the mask? What is the dotted decimal mask that represents /28? And this is the part that maybe is a little bit more challenging, converting from a /28 to a dotted decimal mask. It's 255, 255, 255, 240. Okay? 8 bits plus 8 bits plus 8 bits is 24, plus another 4 is 28. Okay? Which octet am I subnetted in? The answer is the 4th. So the only thing I care about the entire address is 209. That's all I care about. If I want to know the network ID for this host, all I care about is the 209. I don't care about 67, 24, 112. Yes, sir.
Okay, in this example, and forgive me for my stupidity a little bit because it's hard for me to understand the subnetting. If I wanted to divide this IP address or this network into 4, so I will divide the 209 over 4.
No. 209 is not a network ID, number 1. You divide networks, you don't divide hosts. Okay? If you want to divide a network into 4 additional networks, you have to change the mask. You don't change the host, you change the mask. Okay? So you would have to borrow 2 additional bits. Your /28 would become /30 because you follow the formula. 2 to the power of n equals the number of subnets. N is the number of borrowed ones. Okay? The resulting networks you have to figure out. Okay, but you don't simply divide 209 by 4 because first of all, 209 is not a network ID. You know it's not a network ID because it's odd. Network IDs are never odd. They're always even numbers. Because it's binary math. Everything falls on a major binary boundary. In fact, your network IDs will be 0, 2, 4, 8, 16, 32, or some other even type of number. So I'm subnetted in the 4th octet. I take 256 minus the value of the mask in that octet. That gives me my block size. What does that block size mean? Every address in the last octet, because that's the octet we're subnetted in. Every address in the last octet that is divisible by 16 is a network ID. Is 32 a network ID? Yes. Is 48 a network ID? Yes. Is 96 a network ID? Yes. Is 110 a network ID? No. You follow what I'm saying? If the number is divisible by 16, it's a network ID. If the number is not divisible by 16, it is not a network ID. Now, my objective here is to find out what this host's network ID is. I want to know what room that host belongs to. Does that host belong to the 67.24.12.0 subnet? No. Does that host belong to the 67.24.12.16 subnet? No. Does that host belong to the 67.24.12.32 subnet? No. By the way, how do I know those are subnets? How do I know that those are subnets? Because we're using blocks of 16. This is our block size. Every address in the fourth octet divisible by 16 is a network ID. So your best bet, honestly, if you don't want to do a whole lot of math, is to figure out the closest number to 209 that's divisible by 16. Remember, you don't get a calculator for the test, so all of this math you have to do in your head. Is 67.24.12.160 a network ID? Yes or no? Is 67.24.12.160 a network ID? Is 160 divisible by 16?
Yes.
Yes, 10 times, right? So you can simply start there. You can say, okay, the next network, 67.24.12.172. All right, sorry, 176, right? Next network after that, 67.24.12. what? 192? Agree? Next network after that, 67.24.12.208. Guess what we just found? Our network ID. 67.24.12.2. 16 plus 8. 224? You sure about that? Yes. Right? So the thing is, what network does 209 belong to? 209, which is a host, they don't belong to the 160 network. They don't belong to the 176 network. They belong to the 208 network. Isn't the network ID the very first address in the subnet? Yes. What is the broadcast address for that host's network? 67.24.12.223. You guys understand why it's 223? Oops. Do you guys understand why it's 223? Because the next network is 224. And by definition, the broadcast address is always the last address in the subnet. So what is my assignable address range? It's 12.209 through 12.222. That is the assignable range. So that is the entire anatomy of that host's subnet. 67.24.12.208 is the network ID. 67.24.12.223 is the broadcast ID, and 12.209 to 12.222 is the host range. Now, when you start to get good at recognizing these numbers, it starts to just kind of fall together. If I did 172.34.56.21/20, now I can already tell you that the network ID for this host is 48. The broadcast ID is 63. Network ID is 172.34.48.0. The broadcast address is 172.34.63.255. The host range is 172.34.48.1 through 172.34.63.254. Sorry, I missed your question, Ivan, about the 240. I already erased everything. I apologize. Now, how did I get that number? How did I get those numbers in my head? Well, the part that I'm good at, which you guys eventually will get good at if you start to deal with it a lot more, is converting a /20 to the dotted decimal mask. I know a /20 is 255, at least, right? Mm-hmm. But I need 4 more bits. 4 more bits is a 240. You follow me? Yeah. I also know that 256 minus 240 equals 16. So I know that in the third octet, all of my networks are divisible by 16. So my first network is 172.34.00. My next network is 172.34.16.0. My next network is 172.34.32.0. After that, 34.48.0. 172.16, 34. What's after 48? What's 48 plus 16? 56? Is that right? I did my math a little bit wrong earlier. 64? Yeah. 48 plus 16 is not 56. 48 plus 8 would be 56, right? We're doing blocks of 16. So I recognized in my head, oh, a 240, that's a block of 16. The closest number to 56 divisible by 16 was 48. So the network ID was 48. The broadcast, 172.34.63.255. Isn't this the last address in this subnet? Is 63.255 one less than 64.0? 63 is one less than 64. Agreed?
But here's the question. Where do we get the 255 and the fourth option?
Because what's one less than 0? If I said the time is 0 to 59 seconds, what's the next second after 59? It's not 60, it's 0 again, isn't it? But it's the 0 of the next minute. So 1 less than 0 is 255. You see what I'm saying? 1 more than 255 is 0. So my host range in this case is 48.1 through 63.254. The nice thing about this process is it doesn't matter at all where the address is, what the mask is, where the host is. You can change the mask to any number. I could make this a supernet, and instead of saying 20, I can say 12. Now the network ID becomes 172.32.0.0, and the broadcast becomes 172.47.255.255. My block size didn't change. The only thing that changed is where I was calculating the blocks. So now we're in the second octet. So this is what it looks like. Oops. And so on. Basically, you're breaking subnetting down to a single octet. All of your calculations are going to be based on a single octet. And you might look at this and go, well, you know, that's not really allowed. 172 is a class B. It actually technically is allowed. Instead of making the network smaller, you're making it bigger. That's called supernetting. Or if you're using this to do things like routing, summarization, or route aggregation, or whatever. Okay? I know it's a lot of information. Hopefully you'll be able to go back and review the video and it might make a little more sense. People always ask me, what is the best way to do subnetting? And my answer is always the same thing. Whichever way gets you the best answer, the right answer, right? Because there are lots of different ways to do it. Lots of different ways to do these calculations. The challenge with this particular method is being able to go from a prefix notation to a dotted decimal notation. All right? And of course, with any type of math, practice makes perfect. So my suggestion would be to simply just start writing down random addresses and masks and start running through the calculations to see if you get the right numbers and use a subnet calculator to figure it out. All right, we're not quite done with this chapter yet. We still have a little bit to go, but let's go ahead and continue forward. I did in this chapter give you guys several different examples to work from, so you can review these a little bit later on. We've got the 10.45.65.123/27. I know 27 is a 224 in the fourth octet, so I know that I'm only concerned about 123. 224 is a block of 32, which means that my network ID is 96, because 96 plus 32 is 128, which is too much, right? This is the same step, all right? There's my block size. These are the individual networks. I wrote them all down. Here's my network ID, here's my broadcast ID, there's my host range. Oops. Another example here, /29. Now /29 is also in the fourth octet. /28 is 4 bits, /29 is 5 bits, which means I have block sizes of 8. If I have block sizes of 8, every address in the fourth octet divisible by 8 is a network ID. The closest thing to 55 divisible by 8 is 48. And you can extend this over to different octets. /19 is 3 bits in the third octet, which is a 224 in the third octet. It gives me a block size of 32. Now I care about 165 because I'm subnetted in the third octet, not the fourth octet. Closest number to 165 divisible by 32 is 160. So that becomes the network ID for that host. Here I've got a /20, which is a 4 bits in the third octet. 4 bits in the third octet means 240. 240 is a block of 16. Again, closest thing to 79 divisible by 16 is 64. Okay? All right. Of course, we also know that traditional subnetting wastes address spaces. Traditional subnetting means every network gets the same number of hosts, meaning that every network has the same mask. But you know, you might have a situation where some networks get larger masks and some networks get smaller masks. This is what we call variable length subnet masking. Variable length subnet masking means maybe one network has a /25, the other network has a /26. But there's something very important that I want to describe about this process. Let's say this is 0 and this is 255. And we're talking about 10.10.10.0/24. So this pi, this circle represents that network. 10.10.10.0/24. That circle represents that network. So this is my /24. Now, if I were to subnet, when you do subnetting, you can't just simply slice out one piece and call that a network. So this is network 1 and that's network 2. Can't do it because the math doesn't work. So when you're subnetting a network, every time you borrow a bit, you're dividing that network in half. So this becomes /25, this becomes /25. Now that's 0 to 127. You borrow another bit. If you do it across, you create 4 subnets, but you don't have to do that. You could simply borrow a bit within that subnet. So this is /26, that's /25. Then you borrow a third bit, that's /27. Borrow a fourth bit, /28/28. Okay? The point that I'm trying to make is that in order to create this subnet here, in order to create that subnet there, I actually had to create all of these subnets. There's no way to have this /28 without having that 28, that 27, that 26, and that 25.
If you were to simply just have that subnet, then you would pretty much just waste all your own.
Right. And these networks would exist. You might say, well, but I just want to take the rest of these addresses and put them together, right, and create one network. Can't do it. It's not possible. All right? So that is one of the restrictions to VLSM. And in addition, every time you create a subnet, you're losing 2 addresses. But we knew that anyway. All right, we knew that already. We can subnet in IPv6 as well. We've already talked about this concept, right? We talked about how a company might get a /48, and they're going to subnet down to a /64. Based on the math, how many subnets is that? Well, I borrowed 16 bits, which means 65,536 subnets. That's what that means, 65,536 subnets. 2 to the n, right? Number of borrowed ones. And then you simply just say, okay, well, there's network 0, there's network 1, there's network 2, there's network 10, there's network 11, there's network 12, all the way up to network 65,536. So the point that I'm trying to make here is that subnetting in IPv6 is no different than subnetting in IPv4. You're just borrowing ones. The more ones you borrow, the smaller the networks become. Of course, in this, it's relative. All right. Now, you don't have to just borrow 16. That was a question somebody posed earlier. You can borrow more than 16. In fact, you can borrow all the way down into the interface ID. The reason why /64 was chosen was because of the EUI64 process. But you're not limited to that. You could make a decision in your network to say, we're going to make every network a /80 because I need a lot more than 65,000 subnets. The downside to that, though, is if you have devices that don't support address assignments, they only do EUI64, they're not going to work because they can only derive the host portion of the address from their MAC address.
For EUI64, is that a process that happens automatically?
It is, yes.
Oh, okay.
Like Windows machines do that automatically. But we generally try to avoid it, right? Why? Because I don't want my host addresses to be 64 bits long. I want my host addresses to be 1, 2, 3, 4, 5, 6, just like decimal. Yeah. EUI64, your host address is going to be something based on your MAC address. Yeah. You know, so we don't really use the EUI64 process that much. We use it for link local because that's, by definition, that's how it works. But you can also statically assign link local addresses. We'll talk more about link local addresses when we start to get into some configurations. I know it was a lot of information, obviously. It's a challenging chapter, and quite honestly, I'll tell you, when people go through this lesson, they don't always get it the first time. They don't always get it the second time. Sometimes it takes a few times. But once you get it, it's there. You won't forget it. Okay? All righty.